Hello, I'm Trent Rosenthal, the founder and CEO of Qubibyte. Today I'd like to make an official statement on three pieces of technology that we've been building: our quantum circuit simulator, a Qubi Programming Language, and QubiAI, an AI-powered code generator for quantum circuits. These are all live and free to use on our website right now, and they represent a significant part of what we're doing at Qubibyte on the software side. When I started working on Qubibyte Quadra, I realized fairly quickly that we needed a proper simulation environment. There's existing tools like Qiskit and Cirq and various browser-based simulators, but none of them were quite right for what we needed. We needed something scalable for our NMR hardware and for future quantum hardware, and something intuitive for developers, because quantum computers should not be programmed through a Python library. The Qubibyte Quantum Circuit Simulator is a fully browser-based tool that lets you design, simulate, and visualize your quantum circuits in real time. It supports drag-and-drop gate placement, block sphere visualization, state vector inspection, measurement probability distributions, and a quantum gate creator. You can export your circuits as images or code, and then import them back at a later time. It's entirely free with no account required. The backbone of the simulator is our Qubi Programming Language, which empowers users to quickly build and simulate quantum circuits. Qubi is a purpose-built quantum programming language designed to be as minimal and readable as possible, while still being powerful enough to express any quantum circuit. I wanted something that a student could learn in 5 minutes, and not something that requires importing a dozen libraries and writing lines of clutter before you can even place a single gate. So here is a bell state in Qubi. There's 2 lines. You can have a Hadamard gate applied to the 0th qubit, and then you can have a CX with the 0 as the control and the first qubit as the target. When you run it, you get a maximally entangled pair, which is the foundation of quantum teleportation, superdense coding, and dozens of other protocols. For comparison, here's the same circuit in Qiskit, and here's the same circuit in OpenQASM, the open standard for describing quantum circuits. All three of them get the job done, but Qubi is designed to stay out of your way so you can focus on the actual physics instead of fighting the syntax. Qubi supports the full standard gate set that you would expect in any quantum framework. You have the single qubit gates, the multi-qubit, the rotational gates. You can easily apply the same gate to multiple qubits in a single line, and for iterative algorithms like Grover's, you can easily perform loops with their repeat statements. So now let me walk you through something a little more substantial, Grover's algorithm. It's one of the most important quantum algorithms, because it provides a quadratic speedup for unstructured search problems, and it's a great benchmark for any quantum language. Here's a complete implementation in Qubi, searching for the state 101 across 3 qubits. It starts with applying a Hadamard gate to 3 qubits, then it repeats the rest of the code twice, where you have the oracle, which flips the phase of the 101 states, and then you have the diffusion operation, which amplifies the state's probability. Running the circuit gives you a 95% chance of finding the key 101 with only 2 iterations. In other quantum programming languages, this circuit requires not only more lines of code, but more characters typed. This is why Qubi now exists. But what if you don't want to write the code yourself? That is why we have QubiAI. It is an AI assistant built directly into the Qubi code editor in the quantum circuit simulator. You can describe a circuit in plain English, something like create a bell state or Grover search for 101 on 3 qubits, and it generates valid Qubi code, loads it into the editor, and renders the circuit automatically. Under the hood, QubiAI currently runs on Cloudflare Workers AI with a system prompt that encodes the full Qubi specification, the gate semantics, and a library of different worked algorithm examples. The model knows that preparing the state 101 requires X gates on qubits 0 and 2. For Grover's algorithm, it knows that the oracle for a given target state requires X gates on each qubit whose target bit is 0. It understands the optimal iteration count as well. And it can generate bell states, GHZ states, quantum Fourier transforms, Bernstein-Vazirani circuits, teleportation protocols, and a lot more. Every response is validated against Qubi syntax rules before it ever reaches the editor. So if the output is syntactically invalid that QubiAI is feeding you, it will be rejected and retried with a more capable fallback LLM. There's also a 10-second rate limit, so hopefully the system is very responsive for everyone who uses it. Right now it's very limited in capacity, and it also has an overall daily limit. so unfortunately it's still very rudimentary. So the current implementation works, but it's not where we plan to stay. Right now, QubiAI relies on a general-purpose LLM interpreting Qubi through a carefully tuned system prompt. That's a reasonable starting point, but it has very clear limitations. A general model doesn't inherently understand the quantum gate semantics or the circuit topology. It's just pretty much pattern matching from the examples that I'm feeding it, instead of reasoning from the first principles. The next step is to fine-tune a model specifically on Qubi syntax and quantum circuit patterns, trained on a curated collection of validated circuits and algorithm implementations. A purpose-built model would be significantly more accurate and consistent than a general LLM trying to parse quantum instructions from a prompt alone. It would also be smaller and faster, since it wouldn't need the broad knowledge base that a general model carries. There's also an autonomy consideration that matters a lot to us. Relying on a third-party cloud provider for core AI capability introduces latency, maybe usage constraints. If Cloudflare changes their pricing, deprecates a model, or experiences downtime, QubiAI will go down with it. So the longer-term goal is to bring inference in-house, either through self-hosted infrastructure or through on-device execution, so that QubiAI runs independently of any external service. That makes the system faster, more reliable, and fully under our control end-to-end. Beyond just the code generation, a fine-tuned model that deeply understands gate behavior and circuit structure opens up a lot of possibilities. It could suggest circuit optimizations, it could identify redundant gate sequences, estimate resource requirements for different hardware backends, and help debug circuits that aren't behaving as expected. That's the trajectory that we're on, and fine-tuning is the critical first step towards getting there. When I started Qubibyte, I said that one of our goals beyond the hardware would be to develop quantum programming languages and software. Qubi and the simulator are that promise being delivered, and they're core infrastructure that will hopefully be developed and useful for years to come. The Qubi language is going to serve as the native programming interface for Qubibyte Quadra. The workflow will be to write and test your circuits in the simulator, which is both on our website and also built into Qubibyte Quadra. And then you can execute that same Qubi code on real qubits. QubiAI takes it further by lowering the barrier to entry. A student who has never written a quantum circuit can describe what they want in English and immediately see it rendered and simulated. That's powerful for education, and it's only going to keep improving. The simulator, Qubi, and QubiAI are all free to use right now at qubibyte.org/simulator. You can build a Bell state or run Grover's algorithm. You can ask QubiAI to generate something you haven't tried before. You can load one of the built-in examples and study how it works. And then you can export as a circuit diagram for a presentation or for a paper. If you're a student, a researcher, or just someone who's interested in quantum computing, this was built for you. So if you have something break, or if you have ideas on how to make something better, I want to hear about it. I'll be releasing a more in-depth video on how to use Qubi within the simulator, so stay tuned.